Okay. Sometimes you need to review yourself and make everything clear. Today, section 12.2, we will study about vectors in three-dimensional space. So in three-dimensional space, a vector is denoted as this. It has any vectors will be like this. A here is the initial point, and B here is the tip or the terminal point of a vector. And we denote it as boldface V here, or we write an arrow on top of it, vector V like this, just notation. Because in writing, we cannot, if you prefer this way, boldface here, in writing, you cannot write the bold letters yourself. So you may need to use underscore like this. It's okay with that. This is another way to write this vector. And okay, vector V is defined as A, B, where A is the initial point, B is the terminal point. So here in the figure 1, vector AB and vector CD, they are equal. And one more important thing about vector is the direction of the vector. Right? Here, if the two vectors, vector V and vector U, they are equal to each other if it has the same direction from here to here, for example, and the same magnitude. Magnitude is the distance from A to B, from the initial point to the terminal point. That's it. Same direction, but they may be placed in different places in the space, right? Okay. The same length and same direction. And the definition of the sum of two vectors. For example, if we're given the vector U is like this, and the vector V is like this, the sum of vector U plus vector V will be the vector connect from the initial point of vector U to the terminal point of vector V. Okay? And this rule, we call it triangle law. From this is U plus V, right? How about if there's another vector V here? So look at this. Vector V here and vector V here are equivalent, right? They're placed in different places. The origin of the vector, the blue one here, the initial point of that is right here. While the second vector V, the vector V here, it has the initial point is right here. It has different initial points, but it points in the same direction and the same magnitude. Therefore, they are equal. So we can use the same notation, V and V here. So if we use this triangle, U plus V, it will give us the purple line here, which is U plus V. Right? If we use V here on the left, the blue one here, then V plus U will give us this V plus U, the sum of them. And that has the same value as U plus V. V plus U is equal to U plus V. And this rule, we call it parallelogram law. Okay. Just some new concepts. Okay. So suppose here, let us do this example. Oops. Let us try to solve the example 1 here. If we are given the vector A and vector B as in this figure, okay? Can we find the vector U plus vector A? A plus vector B. You can write this, or I normally prefer writing this. This implies both in writing. Okay. So this is vector A, right? And this is vector B. So we see that the original one, vector B in blue, and the vector B in green, how are they compared to each other? The one I just created here. The green one and the blue one. Yeah, they point at the same direction and has the same length, right? What I did just I copy this vector here, but I place the initial point of vector B in this position, all right, at the terminal point of the vector A. So therefore, the vector B, we can place it here, right? This way. So the triangle law tells us what is the sum of A plus B according to this figure. A plus B, it will connect from the initial point of vector A point to the terminal point of vector B, right? So it would be like this. Okay, do you agree with that? Just translation and use the triangle point formula. So this is A plus B. Let us write this way. Okay? That's it. That is how we draw it. Okay? So continue. Here, a definition of scalar multiplication. If C is a scalar or a number, and V is a vector, then the scalar multiplied CV here is the vector whose length is C times the length of vector V. Just definition. For example, look at this. Let me copy this definition and bring it down. Here is easier to follow. Here, for example, I give, let us define, this is vector V here, right? So and I call it vector U. According to these two figures, we see that this has 2 units, right, in length. 1, 2. This is 1, 2, 3, 4, 5, 6. So we see that vector U and vector V, they have the same direction, but the length is U is 3 times vector V, right? So or we say that, okay, U is a scalar multiple of vector V, where C in this case is 3. Okay. If this number is a negative number. For example, -3, right? Then -3 in length, they have the same length, right? Yes, but it point in the opposite direction, or this is -3v. Yes. Mhm. Because the length of vector v here is 2 units, and the length of vector u here is 6 units. So, okay, that is scalar multiplication. Or if you look at this figure, figure 8, v is the blue vector here, right? V is right here, pointing in this direction. Therefore, -v is a vector with the same length, but point in the opposite direction. So the green one here is the -v. Do you agree with that? Okay, very good. And suppose vector v is like this. Okay, so look at these two vector. How are they? The red vector, how is it compared to the -v? The same, right? Therefore, this is also -v, right? We can define it this way. Okay. Yeah, we can write it in terms of vector. Okay. So the triangle law tells us that u plus -v will be the purple line here, right? The purple vector. So that's it. These are some concepts you need to keep in mind, and let us continue. It's not difficult. So, and in 3Ds, it's similar to 2Ds in plane, Cartesian plane. In 3D, the components we also write it in this way. Vector A here has 3 components: A1, A2, and A3. In textbook, it is written in the vector is written as boldface. It is bold, and yeah, the component is written as normal, right? In writing, you may consider writing it this way. Or vector A is A1, A2, A3. I'm okay with these two ways. Or you may write it vector A like this. It's up to you. Okay? They're all okay with me. This is a visualization in 2D. In 2D, the plane O, X, Y, the vector from the origin to this point, A1, A2, is defined as this one. But in 3D, it's more general. Okay, like this. And here is very important that the point P, 3, 2 here, is the position vector. So OP is the position vector of the point P, 3, 2 in this case. If the point P here is given like this in the coordinate, then the vector connecting from the origin to that point is the position vector. Okay, just some new things. So just definition, right? Just let us move on. So if we're given 2 points, the point A and the point B, whose coordinates of them are x1, y1, and z1. The coordinate of B is x2, y2, and z2. Then the vector A is defined as the vector from A to B will be the coordinate of vector to the terminal point, subtract the coordinate of the initial point, which is x2 minus x1, y2 minus y1, and z2 minus z1. Some concepts, okay? And here, suppose these are the components of vector A, right? So in section 12.1, what is the distance from A to B? Do you remember the formula? Thank you, Walid. X2 minus x1 square plus? Very good. Plus? Thank you. Very good. So this is the distance from A to B in the chapter 1, right? And vector A, B here has the same length, and therefore it should be square root of A1, A2, A3, where A1 is the first component in the x coordinate. Okay, because we define this vector as vector A, therefore we call it A1, A2, A3. Just notation. Thank you. So these are some concepts. There's nothing very difficult here. So do you have any question? We're good, right? Very good. So let us do this example. Find the vector represented by the directed line segment with the initial point A to minus 3, 4, and the terminal point is B minus 2, 1, 1. So from the previous definition here, what we are doing is to find the vector AB, right? So what is vector AB? Very good. Minus 2 minus this guy is 2. And what is the y component? 1 minus negative 3 or 1 plus 3. Very good. And the last component? Yes, 1 minus 4. So let us simplify it. So you should be very careful with the negative sign here. Oops. If we write it too quickly, you do it in your head, you may got a mistake. So be careful with the negative sign. That is just a reminder. So therefore, the first component will be negative 4, very good. And the second? 4, very good. And negative 3, yes. Very good. So what is the length of this vector? We, in notation, in writing, we can write it in the absolute values like this, or you may also write it this way. So both are okay. So the very good. Thank you, Aluk. Okay. So it will be 16 plus 16, right? Plus 9. It will be 32 here plus 9 will be 41. Okay, that's it. We can stop here with this value. Or it is also the same as -2 minus 2 squared, and then, yeah, blah, blah, blah. Okay. It's not difficult, so let us move on. And here are some properties. A plus B is equal, the same as B plus A. A plus B plus C is A plus B, then plus C here. And A plus 0, 0 is the vector 0. It is 0, 0. Or we can also write it here. Anyway, yeah. And A plus a negative, A will be 0. And a number multiplied with a sum of two vector will be C plus CA plus CB, and similar things here. The one here, 1 multiplied A will be A. So these are simple. And these are basic vectors. So remember, in 3D, there are 3 coordinates, 3 axes, axis X, axis Y, and axis Z here. So I is the unit vector of the OX axis. J, it has coordinate 1, 0, 0. The vector J is 0, 1, 0. It is the purple vector here. And Z and K is the unit vector of OZ, which is 0, 0, 1. So this is a basic, because any vector A in this coordinate, we can write it as the sum of A1I plus A2J plus A3K. Okay. And again, here, if A is not a 0 vector, a vector 0 here, for any given vector A, we can always find a unit vector of that in that direction. So, and that unit vector is vector A divided by the length. That's it. That is called the unit vector. For example, for any vector A here, it has this length, right? Then in any direction, we can always find a unit vector which point in the same direction as vector A. Okay? And it is unit. Therefore, the length of that will be simply 1. Okay? It's a new idea. So these are some new concepts. Let us follow this example here. Application of this. Suppose we need to find the tensions of in T1, T2 as in figure here, of both wires here. And this has a weight of 100 pounds. Okay, it is in equilibrium. So how can we find T1 and T2 if the magnitude of T1 is this big? And the magnitude of T2 is this big. Okay? So now let us break it, examine these properties. Suppose we're considering this in 2D, right? And this direction, we call it X. And this direction, if we call it Y. Okay, let me see. Let us call Y. This is O. Point this way. Okay. Now, any vector in this space, we can separate it into two components, right? That is, okay, the length of T1 is absolute of T1 here, okay? And the length of T2, or let me write it in this notation, is to avoid confusion, okay? And the length of T2 is absolute of T2 here. So let us study this guy. Here, in 2D, we will always able to break T2, the vector T2 into components. Let us call it this guy, T2, let us call it T2x. Okay, this vector. And this guy, we call it T2y. This implies in the y direction, okay? So T2, the vector T2, we can write it as T2x plus T2y. Do you agree? Triangle law. You agree? Very good. And T2x is parallel to the OX axis, right? So, therefore, let me write it down. So it is, so we write the length of T2x here, multiply with the vector I, because, okay, the direction in the x-axis. So it is this, the length of this in the direction I here. So are we okay with that? And T2y is T2y in the j direction. We break this T2 vector into two terms. The first term is in I. The second term is in j direction. Okay? So, Pythagorean theorem and trigonometry. How big is T2x compared to T2? Yes, it's lesser, but how exactly is it? Yeah, if this is theta, right? if this is theta, then T2x will be cosine theta will be T2x here divided by the hypotenuse here, which is T2, right? Do you agree? Trigonometry. Therefore, T2x here, the length of this will be the length of T2 multiply with cosine theta. Do you agree? How about T2y? Thank you. Very good. Okay. And this theta, how big is it? This, right? 32. So let us write it clearly. It is T2 cosine of 32 I plus the magnitude of this times sine of 32 J. Okay. The same story. We can always do this with this guy. Right? T1 here. If this is 30, then this guy is 30 as well. 50, I mean 50. So, therefore, vector T1, we can always write it as T1 in the x direction. Right? Multiply with the vector I in the OX axis plus T1 in the Y direction. Multiply with the unit vector in the Y direction here. But this vector point in the opposite direction, right? Of the OX axis. So it is negative, right? So in front of that would be a negative magnitude of T1x times I. Okay? Write everything clearly here. And we will continue next time to finish this example. Today, I call it a day. See you tomorrow. Wait a minute a second.